and one looks at all functions f of x which are square integrable rather than square summable, and they are square integrable in the sense that mod f of x whole squared dx is finite, and this space is called L2. It is called L2 of AB because the range is A to B, but very often I am going to write L2 of minus infinity as just equal to L2 itself. So if I do not say what L2 is, I do not tell you what the range is, what A and B are, it is understood that it runs from minus infinity to infinity. So this space is going to be of very great importance to us in quantum mechanics, the space of square integrable functions. Of course one can instantaneously immediately generalize it to higher dimensions, so you could talk about functions of x, y, z, 3 independent variables, and then I would write d3r here and mod f of r whole squared less than infinity, that would be L2 with 3 independent variables x, y, z. So this space is going to be of crucial importance to us, and it is a linear vector space, it has got very interesting properties which we will examine, but you have to understand that the only requirement we put on the function which belong to L2 is that they be square summable in this sense. It is obvious that if you have minus infinity to infinity here, it is immediately obvious that a necessary condition for a function f of x to belong to L2 is that f of x should go to 0 as x tends to plus or minus infinity. That is not sufficient, but it is definitely necessary. It cannot go to a constant or increase and then have a finite integral. Okay. So immediately it implies that this function would sort of die down at infinity sufficiently rapidly. How fast should it go to 0 as mod x goes to infinity for this to converge? Yes, f of x should tend to 0 as mod x tends to infinity faster than 1 over x. Only then will this converge. Is that necessary? Is that essential? 1 over square root of x is enough because you are going to square it, so it should go faster than 1 over x to the power half. That is all that is needed. Of course in between it could have some singularities, but they should be integrable singularities. If you had something that for instance if f of x at x equal to 1 behaves like 1 over x minus 1, then you are finished because this integral will not exist. But if it behaves like 1 over x minus 1 mod x minus 1 to the power a quarter or something like that, that is an integrable singularity and things will be alright. So there is no requirement that it should be bounded at all. F of x may become unbounded in between, but it should be integrable. On the other hand, in physical applications, when we apply to quantum mechanics, we will apply this something called the wave function. We would require the wave function to be bounded. We are going to put in extra conditions on it based on physical requirements. Now this space is a very familiar one. Let us look at some of the functions that you could get here in this space. Let us look at L2 minus 1 to 1. So I look at the space of square integrable functions minus 1 to 1. Actually it does not even have to be L2, could be L1, could be integrable, that is sufficient too. But the reason I use L2 is A, because it is important in quantum mechanics, and B, it satisfies, it enjoys a property which is enjoyed already by functions in L2. This space is self dual, its dual is also L2. In exactly the same way, the dual to capital L2 is also capital L2. So the dual vector space would be essentially the same space once again, which is very nice. Okay. Just as similar to a property enjoyed by Euclidean space, it is self dual. In exactly the same way, it will turn out that the space of functions, what is the dual space of functions f of x? Does anyone know? L2 is a space of functions of a real variable x such that this condition is satisfied. What is the dual to this space? It is also a space of some functions. What are those functions? It is self dual, it is also self dual, therefore those functions must also satisfy exactly the same condition. how do you get those functions? How do you get the ones the dual of members of this space here? Yeah, yeah. What transform? Fourier transform. It will turn out it's Fourier transforms. So the Fourier transform, as you know, Parseval's theorem actually in Fourier transforms tells you that this guy is equal to integral dk minus infinity to infinity mod f tilde of k whole squared, where f tilde of k is the Fourier transform of this function here. So this theorem, this Parseval theorem, is actually telling you that the norm of a function of an element of this vector space is independent of the representation. It is exactly the same no matter how you write it. So we will get back to this and see how Fourier transforms emerge here in a natural way. Okay, let us look at L2 of -1 to 1. So we look at those functions of some real variable x defined between -1 and 1, which are square integrable. Now as soon as you say -1 to 1, it suggests that really you are looking at functions of the cosine of an angle, because cos theta runs from -1 to 1, right, that is the range of cos theta, and therefore we are really looking at those functions which are functions of the cosine of some angle theta. But let us just write it as L2 -1 to 1 of x, and we look at all those functions which satisfy -1 to 1 dx mod f of x whole squared less than infinity, finite values. Okay. Now of course let us restrict ourselves to start with, because that is the most convenient thing to do, obvious thing to do, to polynomials. Let us restrict ourselves to polynomials and let us try to find out what these functions are. Now the simplest polynomial I can write down is of course just a constant, x to the power 0, and then I would like to use monomials to build up all possible polynomials. So I would like to use as my initial set of vectors, and let me put this in quotation marks, so psi1, psi2, etc. These I would like to represent by x to the 0, x to the 1, x squared, and so on. Okay. So let us start. Let us start with x0 and impose this condition. In fact the condition that is imposed is slightly different for convenience or historical reasons, for instance, but let us impose this condition and ask what is -1 to 1 dx, and I would like to have the first of these functions, and let me call it f0 of x equal to something or the other, some constant, because x to the power 0 is 1 essentially. So what multiplied, so some constant, let us call it c0, c0 squared, and let us choose them all to be real. This is equal to 1. We have to choose a normalization, but let me initially choose normalization 1, choose everything to be inner products to be 1. This would imply that c0 equal to over root 2. What is C1 then? I use Gram-Schmidt orthonormalization. How do I find C1? Or psi f1, so f0 of x equal to 1 over root 2, and then f1 of x can be of the form some ax plus b. In general it is going to be of this form, it is a linear function, let us choose ax plus b. And what can it be? How do I find what a and b are? What are the conditions I should impose? I should impose the following conditions. I would like to have, since I am doing this Gram-Schmidt orthonormalization, I would like to have phi 1, I use 0, no? Let us call it 0, psi 0, psi 1 and so on. So I would like to have phi 0 equal to 1, phi 1 equal to 1, and I would like to have phi 1 phi 0 to be 0. I would like it to be orthonormal. Okay. And I know, so here is my initial vector in the function space, it is x to the power 0. The other next vector in the function space is x to the power 1, but the most general possibility I can have is a combination of x to the 0 and x to the 1. So I must project out the portion of x to the 1 along x to the 0, and that means I must try to find a and b such that this condition is satisfied. So let us put that in and see what happens. I need to have minus 1 to 1 dx ax plus b the whole squared to be equal to 1, that is this condition here, and I would also like to have the inner product of this function with the original function f naught of x to be 0. And what is the inner product? What is this translated to function space? What does this look like? Integral minus 1 to 1 dx. Phi 1 is represented by f1 of x. So this is f1 of x and the other fellow is f naught of x, and this should be equal to 0. I have restricted myself to real functions. Had I not done so, this would have become f1 star of x, because I do complex conjugate transpose always, but I have left everything real, so this is the condition here. But f naught of x is just a constant, it is 1 over square root of 2 normalization constant, so we will remove that, and this must be equal to 0. So what can it be? Is it an even function or an odd function? It has got to be an odd function. So it is clear that f1 of x cannot have this portion, because that portion would integrate and give you a non-zero number. So this portion is 0, and therefore f1 of x is strictly proportional to x, and then this goes away immediately, and therefore in this equation here you got a squared x squared equal to 1, which gives a squared, and what is this integral? It is twice the integral from 0 to 1, which is x cubed over 3, and therefore it is 2/3 here, and therefore a f1 of x equal to square root of 3 over 2 x normalized. Now we look for f2 of x, and f2 of x is going to be some constant plus something times x plus something times x squared, and you need conditions to determine these three constants. You need three conditions, and there are just about three conditions, because you do want minus 1 to 1 dx f2 of x f naught of x to be 0, you want minus 1 to 1 dx f2 of x f1 of x to be 0, because I want phi 2 with phi naught to be 0, phi 2 with phi 1 to be 0, and in addition you want integral dx f2 of x whole squared to be equal to 1. And the general form of f2 of x is ax squared plus bx plus c, and you have to determine abc, and these three conditions are sufficient to determine abc. It is obvious from here that f2 of x is an even function of x. It is immediately clear that f2 of x therefore will have only the constant term and the square term, x squared term, nothing in between. And what is it going to be finally? Something times x squared and some constant here. Do you recognize these functions? Let me change the normalization. Let us call these functions, Pn of x, they are the Legendre polynomials, and let us write these functions such that the normalization is minus 1 to 1 dx Pn of x Pm of x, where n and m are different integers, should be 0, and when n is equal to m you get a normalization constant. And the standard normalization for historical reasons is 2 over 2n plus 1 delta mn. This is the normalization factor for the Legendre polynomials. So instead of putting them equal to 1, because the way the equations got solved, the differential equation got solved initially, the normalization that is traditionally accepted is 2 over 2 n plus 1. This gets rid of those awkward factors of this kind. And if you recall, P naught of x equal to 1. So it ensures that the first fellow is actually 1, it removes this 1 over root 2 factor, then P1 of x is equal to P1 of cos theta. What is P1 of cos theta? X itself, yeah, P1 of cos theta is cos theta, so it is x itself, so that is easy. P2 of x equal to, yeah, it is 3x squared minus 1 over 2 and so on. Okay. So these objects act as unit vectors in the space of functions which are integrable, square integrable between -1 and 1, and therefore any function can be expanded, any respectable function which satisfies these conditions can be expanded in a Legendre function, series of Legendre functions. Okay. So this expansion in orthogonal polynomials is just a special case of the expansion of an arbitrary function in a linear vector space in terms of a basis set, and we have ensured the basis set is actually orthonormal by doing this. The normalization is arbitrary, you could choose other things and so on. By the way, the most general polynomials that we can define in orthogonal polynomials, we will come across other examples. There are several things that are specified to be specified. The first is the range, I mean, is it a to b, -1 to 1, 0 to infinity, -infinity to infinity and so on. The second is the normalization factor, this factor here, that is chosen for convenience in a specific manner. Pardon me? Pardon me?
Factor be symmetric with respect to n and n?
It is. Why is it not symmetric?
It is only when
it is actually, that's a good point, isn't it? I can write it like that, right? It would be even happier if I wrote this as it is the same thing, no? It is symmetric in n and m, right? Yeah. So it is a normalization factor which depends on the member of the family. I start by saying I am going to choose a basis out of polynomials, so I am deliberately choosing a polynomial basis. Any function which is not a polynomial, if it should not have singularities, if it is unbounded and so on, this will not work, right? If it is a nice function, a complicated function, it does not have to be a polynomial itself, like e to the power x, you write 1 plus x squared and so on and so forth. So it does not have to be a polynomial itself, but the interesting thing is we will come across more examples of this. So the factors that you have to look at are this range, this weight factor here, and finally you might want to have functions defined in -infinity to infinity. Then of course the question of writing polynomials in there does not arise because these will blow up, the integrals will blow up. So you put a weight factor. So it is possible that you have a function, a set of functions which look like -infinity to infinity, d mu of x phi n of x phi m of x star equal to sum a n delta n. So this would be a generalization of what I just said, that there is some weight factor here, I mean there is some normalization factor here, and there is a measure here which ensures that the integrals are finite. A popular measure is a Gaussian measure, so you could put here integral -infinity to infinity dx e to the minus x squared, that ensures that this thing goes to 0, multiplied by these polynomials here. What do you call this? what do you call this set of polynomials, minus infinity to infinity with the Gaussian weight factor there. There is a unique set of polynomials which does this. So again you start the same game, you are saying that you are going to start with the x to the 0, x to the 1, x to the 2 and impose these conditions and you get a unique set of polynomials. What do you call them? They are the Hermite polynomials. These would also appear again and again in quantum mechanics. These are the Hermite polynomials. And then there are instances where you would like to work from 0 to infinity. For example, it could be a radial coordinate or something which runs from 0 to infinity. So you have 0 to infinity, then e to the minus x. There is no need for minus x squared now because it is only going from 0 to plus infinity, whereas in the other case you needed minus infinity, so you put an x squared. What do you call these polynomials? You all studied chemistry 1, right, where they solve the hydrogen atom in radial coordinates, right. What are these functions like? And this set of family is the Laguerre polynomials. Okay, and so on. You can form your own family of polynomials, define your own range, define your own weight factor, and so on. Yeah.
So how do we verify that they are indeed the basis set?
I start by saying I am going to form this basis set out of polynomials. So the way to construct polynomials is to use the monomials as seed, x to the 0, x to the 1, x to the 2, x to the 3 and so on, and then I form linear combinations of these to give me my orthogonal vectors. Yeah. Yeah.
Now how do we verify that every function in L2 can be written as a
Okay. Now the statement is that once you are given a function, once you are given a linear vector space and a basis in that space, then the statement is a function can be uniquely expanded in a unique manner. Every element of this vector space can be expanded in a unique manner in this basis set. That is the theorem in the vector space side of it, because there is an inversion formula that will tell you how to find it. So let me do that. Let us now look at general expansions. Okay. I just wanted to give you instances of these basis set. By the way, even the Fourier transform of a function is really writing a function in a basis set. And you recall that, let me explain how. If you have a periodic function of a real variable such that f of x plus a period lambda equal to f of x, and lambda is generally taken to be 2 pi or something like that, then you write this whole thing in a Fourier series, right, and you can always expand it in the form f of x equal to a summation n equal to 0 to infinity a n cos nx plus b n sin nx. So let us take 2 pi to be the period, and then of course this is true. Now what you are doing here is really to say that a function which is periodic can be expanded in a Fourier series such that the basis set consists of the functions cos nx and sin nx, where n runs over 0, 1, 2, 3 etc. The coefficients are the components of the vector which is represented by the function here. So that is the way to understand it. This is a vector in a certain function space which is a linear vector space. These are the unit vectors in that space, they are the basis set, and this and that are the components of this vector. Now just as the components uniquely determine the function, in exactly the same way the idea here is, subject to certain conditions, once you can make this expansion, instead of specifying the function f of x, I could specify the coefficients a n and b n, and that is it, that specifies the function. Why do I choose n equal to 0 to infinity? Why not minus infinity to infinity? It is the same thing, because sine and cosine have definite parity properties, and therefore it is exactly the same thing. Had I chosen, I could have written this also as summation n equal to minus infinity to infinity, some coefficient c n, and what should I write here? E to the power n I x. then of course you can do this. I combine Cn and C minus n in an even and odd combination and I call them An and Bn. Okay. So this is so for periodic functions. If the function is not periodic, if f of x is defined from minus infinity to infinity and is not periodic, then I cannot expand it in a Fourier series, but I can still expand it in a Fourier integral. So you could still write, even without this condition, you could still write f of x equal to an integral minus infinity to infinity dk e to the I kx plus or minus, it does not matter, f tilde of k. Could still write it in this fashion. Now what is the basis set of vectors? It is a continuous basis labeled by, it is labeled by k, it is labeled by n here. The basis vectors are labeled by n, the basis vectors are labeled by k, but it is a continuous variable, so you need an integration over k, and these are like the unit vectors. Okay. Those are like the unit vectors, and then f tilde of k are like the components, which itself is a function, and turns out that the components, if f of x is in L2, then f tilde of k is also in L2. But for writing a Fourier transform you do not need the function to be in L2. What is the condition you need for a function to have a Fourier transform of this kind? F of x should be integrable, it should be in L1, it should just be integrable, and then this is sufficient to do it. But then there is no guarantee that f tilde of k is also in L1 because it is not self dual. In general it is not, that is the whole point. In fact we know from the theory of Fourier transforms that if f of x is very compact in a finite range, then f tilde of k will have all possible k's, it will be expanded, it will be a function which is not compact, does not have compact support, and the more tight f of x is, the broader, so to speak, f tilde of k is. The ultimate of course is reached when f of x is just a single, has measure, has support only at one point, a delta function. What happens to f tilde of k? It is flat, it is constant, from minus infinity to infinity it is just constant there. So Fourier transforms enable you to actually expand functions which are more than functions, even generalized functions like distributions, like theta functions, delta functions and so on. But if this is in L2, then so is that also in L2. Okay. What's the orthogonality relation in this space of functions which are integrable, and I write Fourier transforms? What is the orthogonality relation? Well, clearly I should write just as, let me give some examples. Suppose I have a set of functions phi n of fn of x, n equal to 0, 1, 2, etc., which forms a basis in some function space, say L2 0 to 1, minus 1 to 1, whatever it is. And let us suppose this is an orthogonal basis, orthonormal basis. What is the orthonormality relation? What would be orthonormality in this case? And let me write down the general cases here. Phi n, phi m equal to delta nm, and summation over n, phi n equal to 1. This is orthonormality and this is completeness. I need to impose those conditions, I need to write these conditions down in the function space, and the function space has a basis fn of x and say some range a to b or something like that. What is the orthonormality relation? It will clearly be an integral dx fn of x. Let us put a more general case, fn star of x m fm of x from a to b equal to Kronecker delta. This is orthonormality. What is completeness? Well, remember in completeness you have to now not integrate. I mean this guy here, this inner product was defined in this fashion here as an integral. What is completeness? I need to have the unit operator appearing, but the unit operator in function space, in such that when it acts on any function it reproduces the same function at every point. So what should be the analog of this relation here? If you understand that, then the rest of it is completely trivial. You agree this is the orthonormality relation? You agree? This is only a matter of getting used to the notation here. What would be the analog of this? Clearly there has to be a sum over n. I mean that is the whole point here. So you start with the sum over n. Okay. And then what? Well, tell me if you believe this. Yeah, it's f. You had different n and m here, remember, and it gave you a delta function there, Kronecker delta, whereas completeness has exactly the same n. So fn star of x. Well, tell me if this you believe this, fn of x prime equal to delta of x minus x prime. Because if I take the right hand side and integrate over x prime over an arbitrary function psi of x or psi of x prime, I am going to produce psi of x. So it is the analog of the unit operator. Isn't this true? If I take an arbitrary function and do dx prime delta of x minus x prime, this is what is meant by saying a unit operator acting on the function space produces the same function once again. So this quantity here plays the role of the unit operator in function space. This is completeness. The summation is over the argument here. The summation is over the index here, and the arguments are different, and it produces the analog of the unit operator in function space. So you have to check both these relations when you have an orthonormal basis, and I mentioned that these two are different properties really, but when translated to function space this is what they look like. And you might have noticed that when you look at orthogonal polynomials, not only do you have this condition, but you also have something where you sum over n. For example, summation Pn of x, Pn of x prime gives you something times a delta function on the right hand side. Now in the theory of differential equations of second order, that itself is part of a more general relation, and this is absolutely beautiful, the theory of the special functions and so on. Even in the case of Legendre functions, this is part of a more general relation, and what it is telling you, well, I do not know whether I should get into that now. If you look at the Legendre differential equation, for example, you know it has two independent solutions. One of them is a Legendre polynomial and the other one is not a polynomial at all. The other one has got a singularity at -1 and +1, it's got logarithmic singularities, and what do you call that? So there's PL of x, and the second one, the solution of the second kind, the Legendre function, is called QL of x. This is the Legendre function of the second kind. It is a polynomial plus a portion which is looks like log 1 minus x over 1 plus x, so it has logarithmic singularities at the two endpoints. And then this is the polynomial, this part is not, and then it turns out that if you do a summation over L, PL of z and QL of zeta, where L and zeta and L are, you can define these functions for complex variables, then it turns out that this guy here is 1 over z minus zeta, which is called the Cauchy kernel, which is what appears in the theory of complex variables. And now if you take this function has got branch points between -1 and 1 and you take the discontinuity across the branch point, then it becomes a PL. The discontinuity of a QL is a PL and so on, and the discontinuity of this, what is that? If I write zeta equal to x plus I epsilon, x minus I epsilon, what is the discontinuity? What is the, how do you replace this Cauchy kernel? Are you familiar with this at all? Are you familiar with this formula? You can always write 1 over x minus 1 over x minus x naught to be equal to the principal value 1 over x minus x naught minus I pi delta of x minus x naught. You familiar with this formula at all? How many people have studied contour integration in complex analysis, complex variables? Yes, how many have done this? Really? Really? Okay, maybe we should. No, you have or haven't? I mean, this is like. That's okay. You're allowed to forget things. How many people have studied contour integration? How many people know what a complex, what an analytic function is? A function which of a complex variable. I write f of z where z is x plus iy, and I write f of z as u plus iv, and u and v must satisfy certain conditions for it to be an analytic function, and then those conditions are called. So everyone knows this. That's all it is. Everybody has studied this. So why do you say you haven't? You already know it. Okay. People. Okay. Okay. It's one of the, it's the sort of pinnacle of 19th century mathematics. I mean, it still has a lot of rich structure left in it, but you see the whole point is all these functions you study, Legendre polynomials, special functions, polynomials, blah blah, everything, exponentials, they should all be regarded as functions of complex variables. That's the right way to look at it. Then things become easy. For example, I start with the exponential function, I take its symmetric and antisymmetric parts, those are cos hyperbolic and sine hyperbolic. Its analytic continuation to pure imaginary values gives me cosine and sine. So the trigonometric and hyperbolic functions are just analytic continuations of each other. The tan inverse and the log functions are all related to each other, etc. There aren't that many functions. This is basically the exponential, does everything. And then of course integration, various theorems and so on and so forth, everything is completely, the correct way to look at things is as functions of complex variables. A power series, it converges inside a circle of convergence, not on a line or anything. So this is the right way to do it, and I will maybe take a few digressions here and there and put in whatever we need at some stage. This stands for principal value. I don't know if you are familiar with the fact that this is, so you have an integration over some function and there happens to be a singularity at x naught, and you could come along here and you could go either this way and avoid it, or you could go this way and avoid it, and they would correspond to these two guys here. So the discontinuity, the imaginary part is in fact this, because you see if I do this or this, I either get plus I pi or minus I pi by Cauchy's rule. So the difference between the two is like going around fully, and that's equal to 2 pi I times delta. So it's a trivial way of understanding why you get a minus I pi there. But if I did that and took the imaginary part here, the discontinuity, I get a delta function which gives me that completeness relation between PL. So this gets replaced by a PL, and this is called the Mailer formula, this is called the Cauchy kernel. So these are all, there is a very unified theory of these things now, well established 150 years ago, more than that, but they help you a lot. This kind of mathematics is classical mathematics, very classical, but it is very interesting, very important in various applications. So all these electrostatics problems you solve, fluid mechanics and so on, and so elasticity and so on, they are all very easily, very comfortably understood if you have some analysis, complex analysis but we'll use it whenever we need it. Oh, that's surprising. Okay, yeah.
If the base is a T of some vector space V, if some vector space is V, does vector space V contains only finite linear combinations of the bases at V, or we can take even infinite linear combinations?
Now let me come to expansions. We will do this. We will talk about expansions. Yeah, you can take infinite. We will see in a minute. Now let's come back from this function space. We are going to come back to function spaces, but let's come back to the general case and state a few results. If phi n is an orthonormal basis in a linear vector space, given a basis, every vector psi element of V can be uniquely this is important, it is uniquely expanded as in the following form: psi equal to summation over n C n phi n. Okay. So that is the statement, and this could be an infinite dimensional space. So in general an infinite linear combination. What is the inversion formula? The inversion formula would find the coefficient Cn in terms of this psi here. So what is the inversion formula here? This would imply, how do you find the Cn's? Exactly by what we did when you took a vector and expanded it, you wanted to find a particular component, you used a projection operator.
How are we sure that the series is convergent for every possible value of C?
Okay. His question is it guaranteed that every one of these fellows for arbitrary Cn's is inside? So we will look at an infinite dimensional space and then put a condition on this Cn. We will do that in a minute. So what is Cn now? How do I write Cn formally? Yeah, all I have to do is to put a scalar product on this side with some phi m, and then the only thing that fires is going to be the n equal to m here, and that will give you Cm. So this will immediately imply that phi m psi equal to Cm for every m. Please notice we are going to look at complex vector spaces, therefore please notice that the vector you expand is the ket vector. So the coefficients will have this as the ket and this as the bra here, otherwise you make a mistake, it is a complex conjugate if you write it the other way about. That is important to remember in this business. So specifying these coefficients is equivalent to specifying this guy here, but of course there is nothing which tells you that you must have a unique basis. There are many bases. Suppose there is another basis. So let us suppose that there exists another basis in the same space which are chi i's, is also a basis in this space, then the same vector psi could also be written as summation over I, not Cn but some di coefficients chi I. All you must make sure of is that the dimensionality of the space is fixed. So if it is finite dimensional, say 24, then this will run to 24 values, this also will run to 24 values. What is the relation between these two guys? Well, this will imply immediately that di chi j with psi equal to dj. You may very frequently want to change from one basis to another. How would you do that? What is the relation between the Cm's and the dj's? What should I do? I would like to connect up these guys with these coefficients. What should I do? Well, what I would do is to take this basis and say each of these fellows can be expanded in that basis, obviously. So let us do that. Let us write chi I itself to be equal to a summation, and I put a phi m out there in this fashion, sum over m, and what should the coefficients be? What should I use? What notation should I use? let us use some notation here, let us call these h for example, or h is a good index, and it should depend on I, it should depend on m. Okay. So I can certainly do this, and then it is clear that HIM is nothing but the overlap phi m with chi I. Right. It is probably more felicitous to call this HMI, so that you are sure that you write the matrix properly in this fashion. So plug that in here, and what would you get? You would get psi dj equal to dj equal to well, we can plug it into many places. And chi I is summation over m, so let us put summation over m h m I di and then phi m in this fashion. All I did was to substitute for chi I from that thing there. Well, I would like to compare that with this guy here, and they are both sums with respect to phi m's, and therefore I can equate coefficient by coefficient. I have phi n here, so let me change this dummy index to n, and I could write this as summation over n, summation over I, h n I d I. This whole thing is some function of n phi n. Okay. So I take an arbitrary vector, any vector in the space, expand it in the phi basis, expand it in the chi basis, but each of the chi basis vectors can be expanded in the phi basis. I put that expansion in, and here it is. And now, since this is a basis set, an orthonormal basis set, this is equal to that, implies that coefficient by coefficient they are equal here. So it immediately says that Cn equal to summation over I h n I d I. It says this. So it relates one set of coefficients to another set of coefficients, but that relation could have been written down by inspection. You needn't have gone through this entire thing, because what does it say? It is saying, what is this Cn? Cn is phi n with psi on this side, and what is it saying? That is equal to summation over I h n I, but h n I is phi n chi I with di, but di is chi j, chi I with psi. That is all it is. But there is no I here, there is no I there, there is I here, therefore I can take this summation inside, and I could write this as phi n summation over I chi I with a psi there. What is this guy? It is the unit operator by completeness, it is just the unit operator, right? Therefore this is equal to phi n with psi. It is an identity. So if you want to go from one basis to another, all you have to do is to insert the identity in between. You work this backwards, and then you arrive at this relation here. Okay. So this tells you how powerful this insertion of the identity is. Anytime I want to change a basis, I insert the identity in that basis. and I may do it repeatedly in a long calculation, 8 different places I insert a different basis and so on, but I can't go wrong because everything is in terms of the unit operator here completely. So you see, this is a completely, it's a very self correcting kind of notation, you can't make a mistake when you do this. But only thing you have to remember, really have to remember, is that when you expand a vector in this basis, a ket vector in a basis of this kind, please remember that the coefficients have the vector as a ket and not as a bra, because otherwise it complex conjugates, and that is the only crucial step you have to remember. Now suppose we answer this question, which is, suppose this is an L2 space, then it is clear that these things here must have finite norm. Now what is the norm of this vector? Once I make this expansion, this implies that psi with psi equal to the norm of psi whole squared equal to what? All I have to do is to plug this in and work out what this is, and this quantity here implies immediately that psi equal to summation over m Cm star phi m. I use a different dummy index so that I do not make a mistake in summation. So the ket vector psi is this, implies that the bra vector is a complex conjugated coefficient, and then the bra vector is there. Okay. And now I want to find what is psi with psi, so I take this and I apply it to the left of this guy, and I get a phi m which is a Kronecker delta, so only n equal to m is going to be picked out, and this is equal to summation over n Cn whole squared. So this is equivalent to saying that if I have a linear vector space in which I look at all vectors with finite norm, that is the same as saying that if I expand it in a discrete basis of this kind, then the coefficients in this discrete basis belong to little l2, they must be square summable, this must be infinite. For this to be finite, this thing must be finite. Now this tells you the importance of the space little l2, because every time I have a linear vector space, arbitrary linear vector space, and I say I am going to look at all vectors with finite norm, then it automatically implies that when I expand these things in an orthonormal basis, the coefficients would belong to little l2, they would have to be finite, this has to be square summable, that is the condition we need. And this statement is independent of basis, because this will also be equal to summation over I mod di whole square, it is automatically true. In fact, this is Parseval's theorem, which says if you expand a function or you expand it in terms of Fourier coefficients, both of them would have exactly the same norm, the function would have the same norm, that is all it says. Okay. Now this is an important relation, namely once you are given this function, how do you invert this coefficient here? Oh, by the way, if you have a function space which is L2 of minus 1 1, and I write some function of theta equal to summation some CL PL cos theta, L equal to 0 to infinity, some function of theta where theta is running from 0 to pi, and then I expand it as in terms of Legendre polynomials, then what is the inversion formula? This is the expansion, and the inverse formula here, which gives you the coefficient CL, this is equal to 1/2 integral minus 1 to 1 dx. I should not write it in this fashion, I should write d cos theta f of theta PL cos theta. I should really write PL star of cos theta because that is a bra vector, but this guy is a real function, and therefore I just write PL cos theta. That is the inversion formula, if you recall. Okay. All right. The Fourier inversion formula is also trivial. what is that equal to? What does it say about f tilde of k? In terms of f of x. So here is the function expanded, I would like to invert it. What is it equal to on the other side? This is an integral minus infinity to infinity dx e to the power minus ikx. You need the minus there, minus times f of x, and you put a 1 over 2 pi for correct normalization here. Why do you put this 1 over 2 pi? It comes from the orthogonality relation in this problem. What is the orthogonality relation in this case? Fourier transform. This factor sits there, so you have to put that in somewhere. So because of that, you used a delta function there and not a delta function over square root of 2 times square root of 2 pi. You need to put the 1 over 2 pi explicitly, and of course different books would use different conventions. You sometimes have a minus here and a plus there, it does not matter. You sometimes have a 1 over 2 pi here and nothing there, and you sometimes have a 1 over square root of 2 pi here and a 1 over square root of 2 pi there to make it look symmetrical and so on, but it does not matter. But you have to stick to one convention to do this. The next thing to do is to look at operators, because that is really where the real stuff is. So we will define tomorrow what is meant by linear operators in a linear vector space, and then we have to talk about the size of operators, norms of operators, the domain, the range, and so on. So we will do that tomorrow.